Okay, we're looking at the second year Stats and Mechanics book, and we're on exercise 4D. So exercise 4 is on moments, and we're looking specifically at centre of mass. So for question 3, we've got a non-uniform plank. So that tells me that the centre of that the weight of the rod or the weight of the plank is not working through its centre. It's non-uniform. I'm giving its length, and I'm giving the weight of the rod, and it's pivoted at its midpoint. Okay, so let's start to get a sketch of all that. Okay, so I've got the rod AB, it's pivoted at its midpoint, it's 4 meters long, and I don't currently know where, so let's label them as A and B, I don't know where the weight is working, so I won't label the 120 newtons on yet. So the plank is in equilibrium, so that means it's balanced, and there's a child of weight 200 newtons sitting at A, and there's a child of weight 300 newtons sitting at B. By modelling the plank as a rod and the children as particles, find the distance of the centre of the mass of the plank from A. Okay, so I know that the rod is 4 meters long, and I know that that pivot is at the center. So I know that each of those distances are 2 meters. Okay, and then if I also think about it, I know that if the rod is balanced, so if I think just about the moments caused by the child sat at A and the child sat at B, B would move down. So the moment at B, because the distances are the same, but the force at B is greater. So the moment due to B is going to be greater. So that does tell me that the weight of the plank must be over to the left of the pivot. If you got it in the wrong spot, it will still work out. You'll just end up with a negative, and it might get a little bit confusing, but it would still work. But just from looking at that, as the child at A is lighter, but the distances are the same and the plank is balanced, the weight of the actual beam, the plank itself, must be a little bit to the left of the pivot. Okay, but I don't know what that distance is. So, in fact, let me just look back to the question. So find the distance of the centre of the mass of the plank from A. Okay, so it doesn't really matter. It will work either way. But I'm not going to label that as X. I'm going to label, because that's the distance that I want to find. Okay, so, and I do know as well that the weight is 120 newtons. Okay, so now that's 120 newtons. And now obviously if they were the only 3 forces, the whole plank would be moving downwards. So the other force, there must be a reaction at the pivot. Okay, so if I take moments about where the pivot is, I don't need the reaction at the pivot, but I'm not totally sure how I'm going to do this. So I can quite easily say what the reaction at the pivot is, because just by resolving vertically, R is the only upward force, so that must equal the sum of those 3 downward forces. So the reaction. So I've got that if I need it. Okay, so I'm going to take moments. And again, it's up to me where I take moments about. So I could take moments about A. I could take moments about the centre of the actual plank. I could take moments about B. I could take moments about the centre of mass. I'm going to take moments about A. Like any of those points would work. Probably taking moments about the centre of mass would probably be the worst option, just because you don't know any of the distances, so you have a lot of unknowns in there. But you could do it. So I'm going to take moments about A, but taking moments about the centre of the where the pivot is and taking moments about B would work equally well. Okay, so take moments about A, and again it's in equilibrium, so I know that the clockwise moments must equal the anti-clockwise moments. So let's go through and do the clockwise moments first. So I've got, okay, so I've got this force. So if my pivot is at A, if you imagine a force working downwards there is going to be trying to, that's going to be trying to turn the plank clockwise. So that's a clockwise moment. So that's a force of 120 newtons. And I don't know that distance, so I'm calling that x. I've also got this force here, which is also going to be trying to turn the whole thing clockwise. So you're imagining that it's kind of pinned at A. So if A was, imagine like the center of a clock face or something, and this was one of the hands of the clock, which way would these forces be trying to turn? So B would also be trying to turn it clockwise. So that's a force of 300 newtons times a distance of 4, because B is 4 meters from A. It's the total length of the rod. And they're the only two forces that are going to be trying to turn it clockwise, and they must equal the anti-clockwise moment. And the only force that would be turning it anti-clockwise would be that force there. So that's a force of 620 newtons times the distance of 2 meters. So if I tidy that up, I've got 120x plus 1,200 is 1,240. So 120x is 40. So x is a third, I guess. Yeah, so x is a third, or 0.333. Let's go to 3 significant figures, meters. Okay, and again, I can see, does that make sense? Yeah, I think it does make sense. So it's actually, it's a lot closer to A than it looks in my not to scale diagram. So actually it's much closer over here. But yeah, that seems fine to me because there's 100 newtons difference between the weights of the two children. This is only just over 100 newtons, so it does have to be pretty close to A for the whole thing to be balanced. So if I was just sort of thinking that through and checking if I thought it seemed sensible, I'd be happy. And then we can check it exactly, and we've got it.